Morning. Going to try a new format today. So this is a conversation with the Anthropic Interpretability team. I'm going to cover a few important background pieces of information and then go into the actual TLDR for the conversation. So the background information we're going to cover is: who is Anthropic? What is Claude? What is an LLM? What is interpretability? What are features, autoencoders, and dictionary learning? And what is monosemanticity? And then we'll go through some of the big ideas from the conversation and share some of those clips. So the first one, who is Anthropic? So Anthropic is a leading AI company you've probably heard of, with a focus on building AI systems that are safe and aligned with human values. So Anthropic was founded and built, interestingly, by a number of ex-OpenAI people. What is Claude? So Claude 3.5 Sonnet is Anthropic's newest language model, similar to OpenAI's ChatGPT. According to many benchmarks, Claude 3.5 Sonnet is now the best LLM on the market. As part of Anthropic's push to build safe and aligned AI, they're also now recognized as the leaders in the field of interpretability, which we're going to discuss. Before we discuss interpretability, just a quick one on what is an LLM. So on the surface, your preferred LLM, whether you're using Claude or ChatGPT, it can produce the next word in a sentence and engage in a somewhat human-like conversation. Under the hood, however, there are billions of adjustable neuron-like connections established during training that allow the model to pass information back and forth. A transformer is the current design and architecture being used. So in this process, it learns, or it soaks up intricate details and captures contextual meaning between words. So it's very much up for debate at the moment as to whether the contextual understanding is emergent or simply the product of digesting the entire internet. For more information on this, I created a WTF is a large language model essay, and then I've got another essay on the emergence debate, which I'll share and link to. But to get information straight from the source, these are the notes from a YouTube tutorial created by Andre Karpathy covering large language models, and I've also linked to that. Definitely recommend checking those out. What is interpretability? So interpretability is a field of study or a field of research trying to reverse engineer how these large language models are working under the hood. So the billions or trillions of neuron-like parameters that we're talking about that are passing information back and forth make it impossible for us to fully understand or unpack how the models are actually able to produce a coherent-ish output. This is both magical and terrifying, and this is where interpretability comes in. So interpretability, not to be confused with interoperability, is attempting to reverse engineer and understand what is happening under the hood by finding specific patterns in the neurons responsible for creating those outputs. So you can think of a neural net that's running these transformer architectures as being similar to the neurons in your brain, passing information back and forth, wiring together. Two more important to know components before we cover the video review. So what are features, what are autoencoders, and what is dictionary learning? So interpretability involves using tools and methods. Tools like sparse autoencoders, and dictionary learning to ingest information from LLMs, to break it down and map that information into more understandable components or features. These are big words and it gets quite technical, but you just need to think of these as tools and methods that help to reverse engineer how this black box is working under the hood. So features are specific human-like characteristics that the model learns and uses to process and output information. An easy way to think of this is to just imagine there might be a veganism feature. So the model is actually able to map meaning between words like vegan, like leather, like animal cruelty. It's able to map all of these things together in some contextual way that we don't fully understand, which is wild. And the last one, what is monosemanticity? So you might hear this term, toward monosemanticity. If we break down monosemanticity, we get something like singular meaning. So when you hear the term working towards monosemanticity in AI, it's just referring to the pursuit to make sense of the black box by extracting understandable features and making them more singular to understand. For example, if you compare the words bank and triangle, bank could mean a place to store, debase your money, the side of a river, or to tilt an aeroplane, multiple meanings, whereas triangle usually means a shape with 3 straight sides and 3 angles. So this is further towards the monosemanticity end of the spectrum. This is what they're trying to do with interpretability, to take the confusing black box, the vast array of connections, and find singular patterns that make it easier to understand. All right, so they were the things that you needed to know. Anthropic, Claude, what is an LLM, interpretability, features, autoencoders, and monosemanticity. Now we can go to the big ideas from the conversation. So this is the conversation here. I'm just going to go through 3 big ideas. So the 3 big ideas were the most interesting parts of the conversation anyway, for me. So the first is doing computational neuroscience. The second is finding the veganism feature. And the third is it's just surprising that it works altogether. So let's look at the first one.
Modeling to be done. But here we're essentially doing like computational neuroscience on an artificial mind. And no one's ever done that before in history because these things have never existed. And no one's ever done, we're like among the first people right now to ever have access to artificial minds this big with the amount of computational infrastructure that it takes to analyze them. We're literally like trying to figure out how these things think. We're studying cognition in a very quantitative way. And that's...
To me, this is the most interesting part of artificial intelligence and interpretability. Through understanding how it works, we're almost certainly going to learn and uncover more about human intelligence. And you can expand this into other realms, like philosophy of mind and every other imaginable aspect of life and intelligence. The second TLDR is the finding of the veganism feature.
I remember first finding this veganism feature that it was really cool, and I did not expect to see it. It was not even the biggest model, and I'm not a vegan, but disclaimer. But it was really interesting to see that this same model could identify the concept of not eating meat, of being worried about factory farming, and not wearing leather, but also in a lot of different languages. And the fact that it was able to tie all of these concepts together was I couldn't believe what I was seeing. The model actually...
So the veganism features a demonstration of language model's ability to map the contextual meaning, i.e. the model is able to connect not eating meat, not wearing leather, and factory farming. It can tie all of these concepts together. The third part is it's just surprising that this kind of research works at all.
Whereas if the original vector had 1,000 components or something, it might not make any sense. And the basic bet we made here, which is shocking to me that this worked at all, was we took some of the latent states, the vectors inside Claude, trained a sparse autoencoder to see if we could represent those as a sum of just a few pieces each time. And the answer was yes. And then when we looked at each of those pieces, they were shockingly interpretable. From a math perspective, I think a sparse autoencoder is really simple. There's just 2 matrices involved. From an engineering perspective,
there's quite a few big words in there, but what he's basically saying is they're able to extract some of the model's internal working memory. You can think of it, the models as like having an internal working memory, the same as you do with your brain and with your memory. And then training a tool, a sparse autoencoder, and using that tool to recreate specific features. When he says vectors, he's basically explaining this process by which the models or the transformers are able to take words, convert them into tokens, and then map those tokens into a higher dimensional space. It's hard for us to conceptualize, but this is how it's able to map meaning between words. And by using this tool, this sparse autoencoder, they can recreate this process. And he shares that while the engineering wasn't necessarily easy. The results were shockingly impressive. Like, they were able to recreate the desired features with incredible accuracy. I've also linked to the Golden Gate Bridge feature, which is another really good way to understand how this works. So final thoughts on this is just this crazy idea that these models aren't some pre-programmed instruction manual, or there isn't some pre-programmed instruction manual on how the model should work or produce an output. So it's not simply regurgitating information from training. This is now obvious. It's just a very flexible structure with billions of adjustable parameters, allowing the models to soak in context and meaning by mapping words in this high-dimensional vector space that we don't have the capacity to fully understand. It's going to be super interesting watching how interpretability research evolves over the coming years. There's this broad idea floating around that as the models get more powerful and are fed more and more training data, interpretability is going to have to innovate and evolve. We're going to have to use these AI models to interpret themselves. And we're no doubt going to uncover some wild and wacky shit on the path to dissecting this increasingly intelligent alien brain. And I've shared all of the resources here. I'll also put them in the essay and link to them in the notes. Peace.